Welcome, and here we're on lesson 5.2 and 5.5 today. We will be working with absolute, get this pen working, absolute extrema today. So we have looked at relative mins and maxes. Today we're going to discover some things about the absolute mins and maxes. So we're familiar with the first derivative test. We have also looked at second derivative test for concavity, but we haven't discussed second derivative test to find local extrema. That is coming up. So this is just, a little bit out of order for that. But however, it's not totally necessary for us to have that today. However, a local extrema may or may not be the most extreme value. The greatest value of the function is called the absolute or global, and the least is called the absolute or global min. If I look at the graph over here on the right, I can identify the absolute max, which is the point A, and the absolute max, which is point B. It's interesting to note that point B is also a relative min. So for that one, it is both a relative and absolute. It occurs in the interior of the interval where relative mins can be identified. However, we also have this property or this possibility that an absolute min or max can occur on the endpoints. So today we're going to take a look at how to discover where it's at. So both types of extrema are important in calculus. Both types of extrema we might expect the process to be similar in how we find absolute extrema, but it's important to note that generally we cannot use the first derivative test alone to find or justify an absolute extrema. So if f is a continuous function on the closed interval a to b, then f has both an absolute and an absolute minimum value and an absolute maximum value. Here they are. This theorem is giving us a guarantee. It will have both. So as long as we're on a closed interval, we are guaranteed that it's going to have both a min and a max. Every theorem we know has conditions that must be met. We can only apply this theorem if our conditions are met. And what are those conditions? Well, we just talked about it, how it has to be a continuous function on a closed interval. If these conditions are met, then we are guaranteed that f will have an absolute min and an absolute max. All right, on with the show. Pause if you need. Example 1. Let's look at why we must have a closed interval, okay? So example 1, I'm looking at the first graph. Is f continuous on the closed interval? Yeah, it sure looks like it, doesn't it? I don't see any jumps or breaks in that curve. Can the EVT be applied? Well, yes, it can, because it also had those closed intervals. I didn't read the second part of that first box, did I? Does f have a min and or a max for this one? Yeah, it does, doesn't it? I can verify right here we have an absolute max, and right here is our absolute min. The absolute max is at, I was hoping that would click. The absolute max is 3 located at x equals, let's just say it's at -1. It looks roughly there, doesn't it? The absolute min is -1, and it is located at x equals -3. On to the middle. Is the function continuous on the closed interval? Well, we would have to answer, whoopsie, we would have to answer no on this one, wouldn't we? It's not closed. So it's not a closed interval. It is continuous. Can the EVT be applied? No, not if the conditions aren't met. Does f of x have an absolute min and an absolute max? Well, let's go look. I see an absolute min there. Ooh, does it have an absolute max? I would hate to try and figure out what it is, right? To try and name it. Because if I put my dot, trying to put a dot right close to that open interval, then somebody else is going to say, but I can get a step closer to that open interval, and somebody else is going to come along and say, you know what, I can even get closer to that open endpoint. So we have to answer that no, we don't have an absolute max. So let's just fill in what we do know. The absolute min looks like it is -3 located at x equals -1. So definitely, we still ended up with one absolute, but not both. But also, we didn't have the guarantee because the theorem for EVT does not apply on this one. All right, the next function I'm looking at, is it continuous? Well, when I trace over it, it sure doesn't have any gaps or anything like that. It does have closed intervals, so we'd have to answer yes. Can the EVT be applied? Yes, as long as the two conditions are met. Does f of x have a max and a min? Well, it's sure better because by the EVT, it says that there will be, as long as we're a closed continuous function. All right, so we should say yes to this. And let's go look and make sure. So I see an absolute max at two locations. There's an absolute max of 4 at -3 and at x equals 3. And then there's an absolute min of 1 located at x equals 1. Perfect. So you can see how if it is a closed continuous function, you definitely will have an absolute min and a max. So candidates test for absolute extrema. This is what the AP expects you to do to prove that there is an absolute max or min when given a function. Find the critical values for the given interval. Then what we're going to do is create a table that will include those critical values as well as our endpoints, because we can see that the absolute extrema can occur inside the closed interval or on an endpoint. All right, so we've got that. When finding the absolute extrema, we'll take our critical values as well as our endpoints and plug that x value into the function equation, which is the original function, the y equals or the f equals. The greatest value, that would be a y value, the greatest y, looks like g, doesn't it? The greatest y value is the absolute max, and the least y value is the absolute min. Give the absolute max and min using the following wording. So if I had to describe it, I would say the absolute max is some y value located at x equals some number. The absolute min is also a y value located at an x location. Note, the following are all equivalent statements. When we say, I wanted to see if I could get to a highlighter. When we say an absolute maximum, we know what we're going after. Global maximum means the same as absolute. If I just use the word maximum, that implies that we're looking for the absolute. Implies absolute. What is the maximum of? Yeah, find the max value. What is the max value? Where does the max value occur? Then they would be looking for an x value. All right, so example 2, let's walk through how to do the candidates test. So we have a parabola here, and I know that a polynomial, this is a polynomial. So from that, I can conclude that I have a continuous function. And I notice too that I have a closed interval. Since the hypothesis for the EVT are met, the EVT theorem applies, doesn't it? I'm guaranteed a min and a max. So looking back on our little table, it says find the critical values. Okay, let's go after our critical values. So to do that, I'm just going to write critical values. We need a derivative, and we need that derivative to equal 0. So let's indicate that that's what we're after. So 0 equals 4x minus 8. Oh, that's kind of nice. And factor out a 4, because usually you want to try to get to a factored form. And that gives us a critical value at x equals 2. I also have endpoints because we're on a closed interval. I have endpoints of 0 and x equals 3. Oops, that's a 3. Now we're going to create our candidates list. Why is it called this? Because it's all the possible candidates. All right, I'm going to just make a table out of this. And in my table, I'm going to list my x value. And then I'm going to calculate out what f of x is. And then I should be able to identify whether that's a max or a min. We just have 3 points. That should be big enough. So points I'm interested in: 0, the endpoint, 2, the critical point, and 3, the endpoint. Now I'm going to look at f of 0, and I'm not going to the derivative. No, no, no. We are going to the original function because we want to know what is the height of the function when x is 0. And I put it in, I'd have 0 plus 0 minus 0 plus 1. Looks like this turns out to be 1. Let's evaluate f of 2. Putting in 2, I'd have 4. 4 times 2 is 8. 2 times 8 is 16 plus a 1. That's a 9 minus 16. That's a negative 7. And then finally we have f of 3. 3 squared is 9. That'll be an 18 minus a 24 plus 1. That would be a 24, a negative 24 plus a 19. Sounds like a negative 5. So let's evaluate our extrema. And I can say without a doubt that this is my absolute min, and this is my absolute max. If I needed to write a statement, my statement written out would be the absolute, do I want to start with max? The absolute max is 1 at x equals 0. And we're so used to saying y, but that table that we just created is our y. You know what? You might even want to put in your table, just so you can remember where you got those values. You can throw the rest of that function there. And then let's say the absolute min is, what was it, negative 7, and it occurred at x equals 2. Get the hang of it? Let's go try another. A little quotient rule for us. Yeah, we need practice on taking the derivative, don't we? All right. This is not always continuous, is it? So our domain, because it's important to understand whether we have a continuous function. Our domain is all reals except x cannot equal negative 3. But negative 3 is outside of our closed interval. Since we have an interval from negative 2 to 1, h of x is continuous on negative 2 to 1. And we have a closed interval. So EVT applies. Extreme value theorem applies. All right, let's get to work. Let's go find our critical values. We do that how? That's right, we take the derivative, set it equal to 0, and find it from there. Now, this one, I expect we might have an undefined value too. So I'm going to include that in my critical value analysis. Let's get h prime of x. H prime of x equals derivative of the top times the bottom minus derivative of the bottom times the top all over bottom squared. If you need to review your quotient rule, take a moment, hit pause, and go do that. Simplifying this, I would have a 2x squared plus 6x minus x squared over, don't expand the bottom, you'll be better off in factored form. And finally, that's going to get me down to what, an x squared. Is it okay if I just cancel? I don't like you guys to cancel it out, so I won't either. What's the harm in just taking a little more space? Now we can factor out an x, and that'll leave us an x plus 6. See if you can identify our critical points. Write them down. Hit pause and write them down. Our critical values. Well, there are 3 of them. We have when h prime of x equals 0, I'm picking up h equals 0 as well as h equals negative 6. That's coming from our numerator, isn't it? And h prime of x undefined, don't write equals because it's not really an equal scenario, but it does occur when x equals negative 3. See, if we say it's equal, then we're saying it's equal to a number, and undefined isn't necessarily a number, it's an idea, right? So we just leave it open and just say h prime is undefined. All right, these are our 3. We also had endpoints because we were on closed interval, right? And our closed intervals tells us to take a look at x equals negative 2 as well as x equals negative 1. This will be a little bit larger candidates table. All right, I think I'll be fine there. So creating my candidates table, I want x, I want my function, was it h of x, darn it. H of x was equal to that quotient of x squared over x plus 3. And we might as well list them out. I'm going to start with, oh, darn. I was just looking, I was going to list my endpoints, which are negative 2 and positive 1. Correct that there. So I'm going to start out listing, let's get a different color, my negative 2 first, but I'm only going up to 1. So this gets canned and that gets canned because they're not in a negative 2 to 1. Yeah, that makes less work for us, doesn't it? So then we got 0, and we also have to look at 1. Okay, a little bit easier than what I was originally thinking. And all right, I think we can close that up. Let's do our analysis. So h of negative 2 turns out to be a 4 over 1. Oh, that's 4. That wasn't too bad. H of 0 is 0 over 3. Is that a defined value? Yes, it is, but it's not 3. It's 0. And then finally, let's throw 1 in. H of 1 equals 1 squared over 1 plus 3. That gets me 1/4. Have you identified your absolute max and min? Hope so. Pretty easy, isn't it? We have a max of 4 and a min of 0. 1 occurred on an endpoint, 1 occurred in the interior, and then we could write our statements, couldn't we? Get erased here. All right, so my statement would say h of x has an absolute max of, this will be our y value, 4 at x equals negative 2. H of x has an absolute min of 1. Nope, it was 0. Of 0 at x equals 0. That's it. All right, I'm going to continue with example 4 on a next video.